Let's see how Babylonians solve two variable equations here. X plus y equals 13 over 2 and x times y equals 15 over 2. What we know is when we add two numbers, we get 13 halves. When we multiply them, we get 15 halves. So what are these two numbers, x and y? By the modern way, we probably will use substitution. For example, from the first equation, we can solve for x. X equals 13 over 2 minus y, and then we will replace this y in the second equation by 13 halves minus x, and then we get if we distribute using algebra, we get a quadratic equation, and then we can use either factoring or quadratic formula to solve for x and y. To solve for x, and after we find x, we can get y by substituting x by whatever the number we get. So this is the modern way, but what we need to do here is to use Egyptian's way. And to understand that way, we're going to, it's sort of like what we talked about before, the false position method, and we're going to try to use some observation. When we add two numbers, for example, if we add x and y, these two numbers, if we get a 3, and it's obvious that one of the numbers should be bigger than half of 3, the other is going to be smaller, or maybe they're equal, two halves. So half of 3 plus half of 3, that is exactly equal to 3. So that's one of the possibilities. If we don't know anything about x and y, if we don't have any other requirements for x and y, there could be infinite many solutions. So that's just one of the possibilities. But it could be a number, if it's a number, say 2, bigger than 3 halves, and then the other y has to be smaller, because if both of them are bigger than half of 3, when you add them, they're definitely going to get a number bigger than 3. You're not going to get 3. So this is what they used. They don't know if x and y are going to be exactly half of 3, but we can assume this x right here is, well, I guess I'm going to first use this example. We can assume is some number is 3 halves plus a z. What is z? Z is just a number. And y as 3 halves minus z. Why can I do this assumption? Because like we said, one of the numbers possibly is going to be bigger than 3 halves. So that's why we add a little bit. And the other number possibly could be less than 3 halves. And so we subtract z. And if you add these two, use algebra, 3 halves of 3 halves plus z, that's x, plus 3 halves minus z, and you will be able to cancel z minus z, and you just get 3 halves plus 3 halves. That's exactly 3. So this assumption is reasonable. But z could be 0. What is z? We may get a small number, or maybe z is just going to be 0. If z is 0, we actually get x, y both equal to half of 3. So this method will work. So we're going to go back to the example, because in our example we have some fractions, but the idea is similar. So what we do is first we assume x. We look at the first equation. We're not going to do substitution. We're just going to assume x is going to be half of this, the sum, half of 2 is going to be, so you times another 1/2. By multiplication of fractions, we get 13 over 4 because straight across. And we assume x is going to be a little bit bigger than half of 13 over 2, and y is going to be a little bit smaller than half of the sum. So you get these assumptions. And we're going to plug both of them into the second equation. Now it's like substitution. So we're going to replace x with 13 over 4 plus z and y with 13 over 4 minus z equals 15 over 2. Now use algebra for a rule or distribution. 13 over 4 times 13 over 4 plus 13 minus positive times negative, we get negative 13 over 4z. Positive times positive, we get a positive 13 over 4z. And positive times negative, we get negative z squared equals 15 over 2. And clearly here, these two cancel each other. So if you realize you're multiplying two conjugates here, you can use the difference of two squares formula without doing this much work. You will just get this and that immediately. So if you learn that formula in algebra class, you can use it directly without doing these two here. Well, if you don't remember that difference of two squares formula, you can still use FOIL rule or just distribute. Okay, so the first part right here, 13 times 13 over 4, you will get 169 over 16 minus z squared equals 15 over 2. So we continue to use algebra, subtract 15 over 2 from both sides and add z squared to both sides. So you get 169 over 16 minus 15 over 2. So we pretty much move this to the left and move this to the right. So we get our variables on the right side. And the left side, we do subtraction of fractions. Times 8 times 8. So we get a common denominator 16. The top is 169 minus 15 times 8. It's 120. Simplify it further, we get 49 over 16. So what we end up with is z squared should be equal to 49 over 16. And what is z? So that if I rewrite it here, z squared equals 49 over 16, what you need to do is you take square root of both sides. From algebra class, you will get z equals square root of 49 over square root of 16, which is 7 over 4. So now we can plug both back here for z. So z is 7 over 4, and this is 7 over 4. So simplify it, we get 20 over 4, that's 5. And 6 over 4, that is 3/2. And we can double check our answer, because when we add 5 and 3/2, that's exactly 13/2. And when we multiply 5 and 3/2, we get exactly 15/2. So that means our answer is correct. So the idea probably is not much different from the substitution we do now. Instead of assuming x and y to be two different values, you can go ahead and just subtract x from both sides or y from both sides to get one of the variables and plug into the other one without doing the assumption. The reason they do this is, again, this idea behind them are similar. They want to get one variable z. They don't want just one variable, so they don't have, after you plug both of them into the second equation, you only have one variable z. You're not going to have both x and y. And that's how we use the Babylonian way to solve two variable equations. So when you do the homework, use this way, not the modern way.